the set here, here and here, they may be totally disconnected, not related at all. Like one might be numbers, the other's rotations, or whatever. Okay. And so the binary operation of any two elements in your group, your set. So A binary operator B here at this position. So this position is A binary operator B. Now this is group 1, so here's your binary operator little circle, and yeah, that's what we're used to. Now here we have a second group, and let's say take any two elements, members of that group, of that group set. Let's say big A and big B. So here will be the element that results from the binary operation of big A and big B. So A binary operator big A, binary operator big B. Okay. Now look, the binary operator here I've made as a filled in, a solid circle. Now this binary operator here is hollow, and I've made this one solid, filled in, because the binary operations are often quite different, right? So, for example, here it was plus mod 4, and here it was just complex number multiplication, right? So quite distinct binary operators, but nevertheless these two groups were isomorphic, right? So what you'll have here in the group table of G2, the second group, will be big A, this second binary operator, big B. Okay? Now, so if these two groups are to be isomorphic, then what do you need? Like what criteria do you need for them to be isomorphic? Well, one obvious thing is you have to translate to make this group table here identical to this one. You have to translate the member elements into this, right? And that'll need to be 1 to 1. I haven't mentioned it before, but common sense says if you have two groups and their orders, in other words the number of elements they have, if those two groups, if their orders are different, different group orders, then they can never be isomorphic, right? So it's sort of so obvious it's almost not stated, but for two groups to be even candidates of being isomorphic, they must have the same size, the same order, same number of elements. Okay, so the first thing you do is you map or translate the elements of your first group into the elements of your second group. So this mapping F, and you're mapping the elements of G1 into G2. That mapping has to be 1 to 1. Okay, so in other words, bijective. So in general, two groups, G1 and G2, they are isomorphic if this mapping between them, this translation of the elements of this set into this set, this mapping has to be bijective. Okay? I've done that a lot. So if it's bijective, it's injective and surjective. Right? So in proving this function is bijective, you'll have to prove that it's injective and surjective, and we'll do that in future portions of this lecture. Right? Now, that's not enough. Now, you may be able to translate this into this set into this set 1 to 1. That's not too difficult, especially if when the two groups have the same order. Okay, but what you want is that the tables, every entry in the table corresponds. Like now, A and B, they're just arbitrary members of this set, and here's the result of a binary operation of these two. So it's A little circle B. Now you want that, now if these two tables are to be this identical, you want this to map into that, right? For all entries in your table. So you want to choose an F so that this, so f of AB maps into this one. That's what you want. So f of little a little b, so you map this one into this one, will equal a second binary operator b. But what is this a? Right? This a here, if you're mapping it, if it maps well, this a here will be f of little a, right? And this big B here will be f of little b. So for big A here, you can put f of little a, and for big B, you can put f of little b, right? So there's a second criterion. One is your f is bijective. You can map this into this one to one, so it's bijective. But there's a second criterion, and that is for all pairs, for every entry in your group table, if you map f of that entry, you will get this, right? So that the corresponding positions have to map. Otherwise, if that does not happen, then your two groups are not isomorphic. So this f of this is this, but A is f of A, and B is f of B, with a second binary operation. This is the binary operation of your second group. Okay, so that's the second criterion, and you have to show that that's true for all possible pairs, A and B. Okay, all right. Well, now we can. So we've got a bit of theory. I can move on a little. So this is the first theorem of this lecture. So it's theorem 35. You're told that two groups, G and H, are isomorphic. Right? So here's the isomorphism symbol again. So these two groups are isomorphic. Right? Now, question: If I have, let's say, here's my unit of the first group, and I'll map that, so that'll just be f of e, right? I just map this one into here. But is this f of e the unit of this group? It's not obvious, right? So I'll say it again. Map this unit of this group into this second group. So this e will map to f of e. Okay? And the question is, what you get here, this f of e, is it the unit of this group? Or rephrasing the question a bit, does the unit of the first group map to the unit of the second group? Or rephrasing it again, so if you have two groups that are isomorphic, do their unit elements, do they map? Okay. So in other words, is f of e equal to the unit of this second group? So that's the first part of this theorem, and we will prove after I've rubbed out the board. Oh, by the way, about boards, I'm hoping it's just a question of when my Chinese wife can accompany me for reasons of translation and language and so forth. So we just go and buy a bigger one and a higher quality, so we don't get this problem. I mean, the white here is just rubbing. I don't even use this area anymore. So my board, this old smaller board, is dying. You can see that just by looking at it. Okay. All right. Now look, a similar question about the inverses. Like here's an arbitrary member of your first set. Just call it X. Right? Just any old member of your group. And let's say here's the inverse of this. Now it's a group, right? So every element has an inverse. So here's X and here's minus X, so, somewhere in this table. Now under F, you're mapping. This X will map to F of X, okay? And this X inverse, this is the inverse of that. This will map into F of the inverse. f of this. Okay. Now, similar question to the unit. This here, is it the inverse of that one? Right? Now, that is the inverse of that. Question, is this one the inverse of this? Right? Now, what is the inverse of this? Well, it's just f of x inverse, right? It's just that. Okay. And we want to know, is this equal to the inverse of that? So is this here, right? Is this equal to the inverse of this? So do inverses map between two isomorphic groups? You see a similar question. Does the unit element map between the two groups? Do inverses map between the two groups? And the answer to both questions is yes. And when I'll wipe the board, and I'll stop and wipe the board, and we'll prove our first theorem, Theorem 35, which says the answer to this is yes, and the answer to that is also yes. We will prove that. So I'll stop there for a moment.